lecture, we take up the wave equation and we solve the wave equation under some conditions. What is a wave equation? Suppose that u equals u of x comma t is a function of two variables x and t. U is a dependent variable and it depends on two independent variables x and t. The variable x is called a space variable and the variable t is called a time variable. The partial differential equation u sub tt equals a square u sub xx or a square u sub xx minus u sub tt is called a one-dimensional wave equation. This equation is homogeneous and linear. Since the equation has only one space variable, this equation is called one-dimensional wave equation. In this equation, the constant a square represents the speed of the wave. This equation is an prototypical example of a large class of equations called hyperbolic equations, because in this equation a square u sub xx minus u sub tt equals 0, b equals 0, capital A equals a square and c equals minus 1. If we find the value of b square minus 4ac, we get b square minus 4ac greater than 0. So, this one-dimensional heat equation is a prototypical example of hyperbolic equations. In my previous lecture, I have solved the one-dimensional wave equation without considering any conditions by using the method of separation of variables. In this problem, we are going to solve the one-dimensional wave equation again by using the method of separation of variables under some given boundary conditions. In this problem, we consider a tightly stretched string whose left and right ends are tied and the string is placed along the x-axis only. Here we have to find the displacement of the wave or deflection of the wave denoted by u equals u of x comma t. Here the initial deflection at a time t equals 0 is given to be u equals u naught sine cube pi x by l. Under these conditions, we solve this vibrating string problem. Consider the one-dimensional wave equation u sub tt equals a square u sub xx. Here a square represents the speed of the wave. In this problem, consider a tightly stretched string whose ends are tightly tied or pinned at both the ends. Now, if we plug the string, a wave is generated and we see that this wave must propagate in only one dimension, say along the x-axis. This problem represents the vibrating string problem. Suppose we have a musical instrument like guitar. In guitar, the strings are tightly tied at both the ends. If we pluck one of the strings, a musical note or a musical sound wave is produced. The one-dimensional wave equation mathematically models that propagation of the wave. By solving the one-dimensional wave equation under the given conditions, we find out the deflections or displacement made by the wave. The deflection or displacement made by the wave is represented by the symbol u equals u of x comma t. In our present problem, the string is tightly stretched and tied or pinned at both the ends. The length of the string is say L centimeters. It is in between two positions x equals 0 and x equals L. That means the left end of the string is placed at x equals 0 and the right end of the string is placed at x equals L along the x-axis. Now, the boundary conditions are given by u of 0 comma t equals 0, u of L comma t equals 0. These two conditions represent that at the left end of the string, the deflection or displacement is 0 at any time t. So, u of 0 comma t equals 0 for all t. Similarly, the right end of the string is also tied tightly. So, the deflection or displacement at the right end of the string is also 0. That is our next condition, u of L comma t equals 0 for all t. These two are the given boundary conditions. Next, the initial position at a time t is equal to 0 is given by the condition u of x comma 0 equals u naught sin cube pi x by L. This represents the initial deflection of the string. Similarly, the initial velocity of the wave is given by the rate of change of displacement with respect to time, that is dou u by dou t, the partial derivative of u with respect to time t, that is the velocity of the wave. Dou u by dou t at a time t equals 0 is given to be 0. The velocity of wave at a time t equals 0 is always 0. So, u suffix t or dou u by dou t at a time t equals 0. Altogether, we have 4 conditions. Number 1, u of 0 comma t equals 0. Number 2, u of L comma t equals 0. These two conditions are called boundary conditions. Number 3, u of x comma 0 equals u naught sin q pi x by l. Number 4, dou u by dou t at t equals 0 or u sub t at t equals 0 equals 0. These last two conditions, u of x comma 0 and u suffix t at time t equals 0 are initial conditions. They denote the initial displacement and the initial velocity of the wave. Now we use these four conditions and we solve the one-dimensional wave equation which governs the wave propagation in the tightly stretched string tied at the both ends. We have to study the vibration of the wave in this stretched string. This problem is governed by the one-dimensional wave equation u sub tt equals a square u sub xx. We solve this second order linear homogeneous PDE by using the method of separation of variables. For this purpose, we select a trial solution, that is u of x comma t equals capital X of x times capital T of small t. We suppose that u of x comma t equals capital X of x times capital T of t is a solution of the given one-dimensional wave equation. If we observe in this solution u of x comma t equals x of x times t of t, x of x is purely a function of the space variable x and t of t is a function of a single variable t and t is the time variable. In the method of separation of variables, we have taken that u of x comma t equals x of x times t of t as a solution of the given one-dimensional wave equation u sub tt equals a square u sub xx. U sub tt means dou square u by dou t square. U sub xx means dou square u by dou x square. Since uxt equals x of x times t of t is a solution of the wave equation, we substitute this in the one-dimensional wave equation utt equals a square uxx. Then we obtain dou square by dou t square x of x t of t equals a square dou square by dou x square x of x t of t. On the left hand side, we have to differentiate capital T of t with respect to the time variable t twice. So the LHS becomes x of x t double dash of t. On the RHS, we have to differentiate x of x t of t partially with respect to the space variable x twice. So the RHS becomes a square x double dash of x t of t. So the one-dimensional wave equation becomes x of x t double dash of t equals a square x double dash of x t of t. Now we can take all the t terms on one side and all the x terms on the other side. If we separate all the x terms to one side and all the t terms to the other side, we get 1 by a square t double dash of t upon t of t equals x double dash of x upon x of x. If we observe this equation, the LHS is purely a function of the time variable t and the RHS is purely a function of the space variable x. These two are equal only when they are equal to a constant. So, we can equate this expression to a constant, say lambda. Then we obtain 1 by a square t double dash of t upon t of t equals x double dash of x upon x of x equals lambda. From this, we obtain t double dash of t by t of t times 1 by a square equals lambda and x double dash of x by x of x equals lambda, which implies x double dash of x equals lambda x of x and t double dash of t equals a square lambda t of t. From them, we obtain two ordinary second order differential equations, x double dash of x minus lambda x of x equals 0. Let this second order differential equation be equation 3. We get another differential equation t double dash of t minus lambda t of t equals 0. Let this equation be equation number 4. So, by using the method of separation of variables, we have obtained two second order differential equations, x double dash of x minus lambda x of x equals 0 and t double dash of t minus a square lambda t of t equals 0. Now we consider the solution u of x comma t equals x of x times t of t, which is a product of a function of x and a function of t. Now we apply our first boundary condition u of 0 comma t equals 0. For that purpose, put small x equals 0 in u of x comma t equals x of x t of t. Then we get u of 0 comma t equals x of 0 t of t. It is given that u of 0 comma t equals 0. If we plug in u of 0 comma t equals 0, we obtain x of 0 times t of t equals 0, which implies either x of 0 equals 0 or t of t equals 0. If we suppose t of t equals 0, then what happens? Consider u of x comma t equals x of x times t of t again. Substitute t of t equals 0 here. Then u of x comma t equals x of x t of t becomes u of x comma t is equal to 0. We obtain a trivial solution. We want a non-zero solution. To get a non-zero solution, t of t must not be 0. So we must have x of 0 equals 0. Remember this condition. Next, let us take the solution u of x comma t equals x of x times t of t again, and we use the second boundary condition now. Put x equals L, then u of L comma t equals x of L times t of t, but u of L comma t is given to be 0. Then u of L comma t equals x of L times t of t becomes x of L times t of t equals 0. But here t of t not equal to 0. So we are forced to equate x of L to 0. So we get x of L equals 0. So we applied the first two boundary conditions to the solution u of x comma t equals x of x times t of t, and we obtained the conditions x of 0 is equal to 0 and x of L equals 0. Remember these two conditions. We are going to use these two conditions to get the solution of our one-dimensional wave equation. So far, by using the method of separation of variables, we have obtained two second-order linear differential equations x double dash of x minus lambda x of x equals 0. That was our third equation. Our next equation is t double dash of t minus a square lambda t of t equals 0, which was equation number 4. We don't know the value of lambda. Depending on the values of lambda, we divide our problem into three different cases. In the first case, we suppose that lambda equals 0. Substitute lambda equals 0 in equation 3. The equation 3 was x double dash of x minus lambda x of x is equal to 0. If we substitute lambda equals 0, we obtain x double dash of x equals 0. Similarly, substitute lambda equals 0 in t double dash of t minus a square lambda t of t equals 0. Then we get t double dash of t equals 0. In this case, we obtained x double dash of x is equal to 0 and t double dash of t equals 0. Integrate x double dash of x is equal to 0 on both sides with respect to x twice. Then we obtain x of x equals c1x plus c2, where c1 and c2 are any two arbitrary constants. Similarly, we integrate t double dash of t equals 0 with respect to t twice on both sides. Then we obtain t of t equals c3t plus c4, where c3 and c4 are any two arbitrary constants. Then our general solution gets the form u of x comma t equals x of x times t of t, that equals c1x plus c2 times c3t plus c4. Now we have to apply our boundary conditions to find out the arbitrary constants c1, c2, c3, c4. First consider the equation x of x equals c1x plus c2. Put small x equals 0. Then we get capital X of 0 equals C1 times 0 plus C2, which implies X of 0 equals C2. Previously, we have shown that X of 0 equals 0. X of 0 equals C2 and X of 0 equals 0 give us C2 equals 0. Now, X of X equals C1X plus C2. Put X equals L. Then we get X of L equals C1L plus C2. Here, X of L is 0 and C2 is 0. If we substitute those two values, we obtain C1L equals 0. Here, L is the length of the string. So, L is always non-zero. Because L not equal to 0, we get C1 equals 0. So, C1 equals 0 and C2 equals 0. Then X of X equals C1X plus C2 implies X of X equals 0. If X of X equals 0, U of X comma T equals X of X times T of T. That implies U of X comma T equals 0. So in this case, we obtain U of X comma T equals 0 as our general solution of the one-dimensional wave equation. U of X comma T equals 0 is called a trivial solution. This solution is not at all interesting. We can't do anything with U of X comma T equals 0. So, we proceed to the next case. In case 2, we suppose that lambda is a positive number. Since lambda is positive, we take lambda is equal to k square for some real number k for our convenience. Now consider our equation 3 x double dash of x minus lambda x of x equals 0. Substitute lambda equals k square in this equation 3. Then we obtain x double dash of x minus k square x of x equals 0. Next consider our second differential equation t double dash of t minus a square lambda t of t equals 0, which was our equation number 4. Put lambda is equal to k square in this equation 4. Then we get t double dash of t minus a square k square t of t equals 0. First we solve x double dash of x minus k square x of x equals 0. This is a second order homogeneous linear differential equation with constant coefficients. So we write its corresponding auxiliary equation. The auxiliary equation is m square minus k square equals 0, which implies m plus k times m minus k equals 0. So the roots of this auxiliary equation are m equals plus k and m equals minus k. Hence, the solution of the differential equation x double dash of x minus k square x of x equals 0 is given by x of x equals c1 e power kx plus c2 e power minus kx, where c1 and c2 are any two arbitrary constants. Similarly, if we consider t double dash of t minus a square k square t of t equals 0, its corresponding auxiliary equation is m square minus a square k square equals 0. That gives us the roots m is equal to plus ak and m equals minus ak. So the solution of this differential equation t double dash of t minus a square k square t of t equals 0 is t of t equals c3 e power akt plus c4 e power minus akt, where c3 and c4 are any two arbitrary constants. Now consider x of x equals c1 e power kx plus c2 e power minus kx. Put x equals 0 first. Then we obtain capital X of 0 equals c1 e power k times 0 plus c2 e power minus k times 0, which implies x of 0 equals c1 plus c2. But we have found that x of 0 equals 0. So by substituting x of 0 equals 0, we get c1 plus c2 equals 0. From that, we can get c2 equals minus c1. Again consider x of x equals c1 e power kx plus c2 e power minus kx. Put small x equals L here. Then we obtain capital X of small l equals c1 e power kl plus c2 e power minus kl. But we have already shown that capital X of L equals 0. Then it gives us c1 e power kl plus c2 e power minus kl equals 0. Here substitute c2 equals minus c1. Then we get c1 e power kl minus c1 e power minus kl equals 0. If we take out c1, then we get c1 times e power kl minus e power minus kl equals 0. Since the exponential function cannot be 0, we get c1 equals 0. So we have shown that c1 and c2 are 0. Hence, x of x equals c1 e power kx plus c2 e power kx becomes 0. So, capital X of x equals 0. Consider u of x comma t equals x of x times t of t and substitute x of x equals 0. We obtain u of x comma t equals 0, which is a trivial solution. So in this case also we obtained a trivial solution u of x comma t equals 0, which is not at all a interesting case. So we proceed with the next case. Let's see what is the solution in case 3. In case 3, we suppose that lambda is a negative number. So we take lambda equals minus k square for some real number k. Now we substitute lambda equals minus k square in our first differential equation x double dash of x minus lambda x of x is equal to 0, which was our equation 3. If we put lambda equals minus k square, our equation 3 becomes x double dash of x plus k square x of x is equal to 0. Next we consider our second differential equation t double dash of t minus a square lambda t of t equals 0. If we substitute lambda equals minus k square, we get t double dash of t plus a square k square t of t equals 0. Now consider the differential equation x double dash of x plus k square x of x equals 0. This is a second order linear homogeneous differential equation with constant coefficients. If we write its auxiliary equation, the auxiliary equation is m square plus k square equals 0. The roots of the auxiliary equation are m equals plus ki and m equals minus ki. Here I square equals minus 1. The roots are imaginary roots. Now the solution of x double dash of x plus k square x of x equals 0 is given by x of x equals a cos kx plus b sin kx, where a and b are any two arbitrary constants. Previously, we obtained two conditions. Capital X of 0 equals 0 and capital X of L equals 0. Let's apply those two conditions to this solution. X of x equals a cos kx plus b sin kx. Put small x equals 0, then we get capital X of 0 equals a cos 0 plus b sin 0. Since cos 0 equals 1 and sin 0 equals 0, we obtain capital X of 0 equals a. But x of 0 equals 0. X of 0 equals a and x of 0 equals 0 gives us a equals 0. So the first coefficient capital A equals 0. If we substitute a equals 0, we get x of x equals a cos kx plus b sin kx, which implies x of x equals b sin kx. Put small x is equal to L in this equation. X of x equals b sin kx. Then we get x of L equals b sin kl. But x of L equals 0. So we get b sin kl equals 0. This equation b sin kl equals 0 implies either b equals 0 or sin kl equals 0. If we take b equals 0, what happens? Let us see. Already a equals 0. Now if we take b equals 0, then capital X of x equals a cos kx plus b sin kx implies x of x equals 0. Then u of x comma t equals x of x t of t implies u of x comma t equals 0 because x of x equals 0. If we take b equals 0, we obtained only the trivial solution u of x comma t equals 0, but we want non-trivial solutions. So to obtain non-trivial solutions, b should not be 0. Because b not equal to 0, we must have sin kl equals 0. So b not equal to 0 forces us to take sin kl equals 0. Sin kl becomes 0 only when k equals n pi by l, where n takes the positive integer values. That means n equals 1, 2, 3, so on. Since k equals n pi by l, if we put n equals 1, we get k equals pi by l. If we take n equals 2, we get k equals 2 pi by L and so on. K takes infinitely many values. For each positive integer value of n, we get one value for the constant b, say b suffix n. If n equals 1, we get b1. If n equals 2, we get b2 and so on and so forth. So, if we take our solution capital X of x equals a cos kx plus b sin kx, we have already shown that a equals 0 and b takes the constants bn. So our solution becomes x of x equals bn sin kx. Here k equals n pi by L. So x of x equals bn sin n pi x by L. For n equals 1, we get one solution x of x equals b1 sin pi x by L. For n equals 2, we get one more solution x of x equals b2 sin 2 pi x by L. So on. We have to add all those solutions. This is called the law of superposition. So by the law of superposition, our solution x of x takes the form x of x equals summation sigma n equals 0 to infinity bn sin n pi x by L. Now let's take our next differential equation t double dash of t minus plus a square k square t of t equals 0. The corresponding auxiliary equation is m square plus a square k square equals 0. The roots are m equals plus ak and m equals minus ak. So the solution of the differential equation t double dash of t plus a square k square t of t equals 0 is given by t of t equals c cos akt plus d sin akt, where c and d are two arbitrary constants. The general solution of the given equation is u of x comma t equals x of x times t of t. Now let us substitute x of x and t of t in the solution. Then we obtain u of x comma t equals summation sigma n runs from 0 to infinity b sub n sin of n by x by L times c cos akt plus d sin akt. Now consider u of x comma t equals x of x times t of t. Here we use our next two initial conditions which were given in the problem. Put t equals 0 here. Then we get u of x comma 0 equals x of x times t of 0. Actually, t of small t equals c cos akt plus d sin akt. If we put small t equals 0, capital T of 0 equals c cos 0 plus d sin 0. Because cos 0 is 1 and sin 0 equals 0, we get T of 0 equals c. So u of x comma 0 equals x of x times t of 0 implies u of x comma 0 equals x of x times c. But in the given problem, u of x comma 0 was given to be u of x comma 0 equals u naught sin cube by x by L. If we substitute this value here, we obtain u naught sin cube by x by L equals x of x times c. U of x comma t equals x of x t of t. Let us take this again. Differentiate this equation with respect to small t partially on both sides. Then dou u by dou t equals dou by dou t of x of x t of t. That implies dou u by dou t equals x of x t dash of t, or it can also be written as u sub t equals x of x t dash of t. We have already seen that dou u by dou t equals x of x t dash of t, or u sub t equals x of x t dash of t. But we were given one initial condition that dou u by dou t at time t equals 0 is 0. That means the initial velocity of the wave is 0. If we substitute dou u by dou t equals 0 at time t equals 0, here we obtain 0 equals x of x t dash of 0, or we can write x of x t dash of 0 equals 0. That implies either x of x equals 0 or t dash of 0 equals 0. If we suppose x of x is equal to 0, we obtain the trivial solution only. But we don't want the trivial solution. So we must take t dash of 0 equals 0. Actually, t of t equals c cos akt plus d sin akt. Then t dash of t equals minus c sin akt plus d cos akt upon ak. If we put t equals 0 here, t dash of 0 equals minus c sin 0 plus d cos 0 whole divided by ak. So we get 0 equals d by ak, which implies d equals 0. Hence t of t equals c cos akt plus d sin akt implies t of t equals c cos akt. Now if we put small t equals 0 here, t of 0 equals c cos 0, which implies t of 0 equals c. We can find the value of this constant c by using our previous equation u naught sin cube by x by L equals x of x times c. Now our general solution u of x comma t of the one-dimensional wave equation under all the given conditions takes the form u of x comma t equals summation sigma n runs from 0 to infinity bn sin of n by x by L times c cos akt plus d sin akt. Here substitute d equals 0. Then we get u of x comma t equals summation sigma n equals 0 to infinity bn sin n by x by L times C cos AKT. Here K equals N pi by L. Then we get U of x comma t equals sigma n equals 0 to infinity Bn sin n pi x by L times C cos n pi at by L. This is our general solution for the one-dimensional wave equation u sub tt equals a square u sub xx under all the given conditions. I solved the wave equation without considering any conditions in my previous lecture. In this present lecture, I have solved the one-dimensional wave equation under some boundary conditions and initial conditions. I strictly advise everyone to solve more number of problems to achieve familiarity with the concepts. For further queries, you can contact me through email. Thanks for watching.